Sir.
This one is I have started recording. Okay. Now we will go to the question. And can you see the screen now? And if you see the screen, what is it that you see?
The wave particle duality of C60 molecules.
Okay. And if you look at the article, this is a paper published by this guy, Anton Zeilinger. I assume you can see the mouse.
Yes, sir.
So therefore, this is a paper published by Anton Zeilinger. And this is the experiment. This was done in 1999. This is the experiment. Well, you can see the year here, 1999. This was published. This demonstrated for the first time that C60 molecules, even a heavy object like C60 molecule, has a wave associated with it. And in fact, in the assignment, I had reproduced this experimental arrangement. You see, you have an oven from which C60 molecules are coming out. They are collimated. That means you select only a beam, right? This is the collimator. And then you allow it to pass through a diffraction grating. Don't worry about what it is, but essentially it has slits which are at a distance of 100 nanometers each. And then there is a detector. The detector is actually placed at a distance of, if you look at the problem, the detector is at a distance of 1.25 meters. Yeah, you can see it here actually. So the detector is 1.25 meters behind the slits. So that is the situation. And when they detected the arrival of C60 molecules, if there is no grating, you get just one peak like this. But if you put the grating, that means it is a collection of slits, then you get an interference pattern, which looks like this. Fine? Okay. And what you are asked is, you see here, what is happening is that the waves associated with the C60 molecule is interfering. And this is actually the most important peak. And then there is another peak here and the similar peak on the other side. And you are asked to calculate the separation in space between these two peaks. And if you read from the x-axis is down here. So you see, for example, this will be around this distance, maybe probably around 25 micrometers. So therefore, this will be also at a distance of 25 from the main peak. And so the separation between these two is about 50 angstroms. So therefore, this is the separation between the peaks. And what you have to do is you have to calculate the wavelength that is observed experimentally and compare it with the wavelength that is obtained by de Broglie relation. So with that, let me first calculate the de Broglie wavelength. I have removed the sharing. I will share once again. That is because I wanted to show you some other screen. Okay, I hope the screen is visible now.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So therefore, you see what I am going to do is I am going to calculate the de Broglie wavelength of C60 molecules. And for that, I use a program called Mathematica. Mathematica, you can see it here if you see my mouse. This is Mathematica. The only thing is that you see I use it to do numerical calculations on the screen. So for example, if you look at the first line, this is the definition of joule. Joule is actually kilogram meter square second minus 2. 1 second. And then 1 nanometer, what do I mean by 1 nanometer? It is actually 10 to the power of minus 9 meters. And this is the value of H. H is actually 6.626 divided by 10 to the power of 34 joule seconds. Is that fine?
Yes, sir.
Yes, sir.
Okay, so I do the calculations. See, for example, joule is kilogram meter square second minus 2. That it has reproduced here. Then nanometer is 10 to the power of minus 9 meters, and H is actually 6.626 into 10 to the power of minus 34 kilogram meter square second minus 1. Now I want to calculate the mass of C60. Let me do that. Okay, it says my internet connection is unstable, so I don't know what is going to happen. C60, as you know, has 60 carbon atoms, correct?
Yes, sir.
And one carbon atom has one mole of carbon atom has a weight of 12 grams.
Gram.
So therefore I write 12, but I want to convert that to kilogram. So therefore I divide by 1000, right? This is now in kilogram. Fine.
Right, sir.
This is the mass of one carbon atom. What I want is the mass of 60 carbon atoms. Agreed? Well, it is, sorry, I made a mistake. This has to be divided by the Avogadro number, right?
Yes, sir.
Yes, sir.
So, because one
02.
mole contains, so therefore divided by 6.023 into 10 to the power of 23. So that will be the mass of one C60 molecule. And the velocity of the C60 molecule that is given is already written here. V is equal to 166.
Sir, in the mass,
Yeah.
160 into 0.012, like 60 into 12 divided by 1000 and Avogadro, like 60
Yeah,
molecules. Sir, I think
no, C60 has 60 carbon atoms.
Yes, sir.
It is
One
like
carbon atom mass.
one
12.
carbon atom mass is 12 divided
12.
by 1000 kilogram divided by
Yes, sir.
6.023. Sorry. 1 second. No, this is the mass of one carbon atom. Okay, now I have to multiply this by
60, sir.
60. Thank you very much. And then I have to thank you. I mean, that means you are following, so that makes me happy. So 12 into 60 divided by 1000 is the divided by the Avogadro number is the mass of a C60 molecule, and that is the answer. Fine.
Yes, sir.
Then velocity of the beam. What is given is the average velocity of the beam, that is actually 166 meters per second. So let me say that that is the velocity. You, for the time being, you ignore this particular statement. Then you can calculate the wavelength. Wavelength will be so much.
Yes, sir.
Right? So therefore, if you want, yeah, 1 second. If you want to convert this into picometer, you see 1 picometer is 10 to the power of minus 12 picometers. Sorry, 1 picometer is 10 to the power of minus 12 meters. So therefore, this may be written as 3.33906 picometers. Fine?
Yes, sir.
Okay, well, there was somebody asking a question. What is the question?
Sir, how can we find speed of fluorine molecule? Is it given or not?
It is given. It is
The
given
question.
in the question. You
Oh,
read
thank you, sir.
you read the question. The speed is given. Okay. In fact, they have expertly measured the speed.
Okay,
Is that
thank you, sir.
fine? Okay. Now comes a little bit of theory, and for that I will have to write. Let me see. I mean, this will need a little bit of effort on my. You can see the screen, white screen.
Sir.
Yes,
Yes.
sir.
Yes. So therefore, what I want to do is I want to calculate the experimentally observed wavelength. So here you have the two slits, correct? You can see the two
Yes.
slits, right? And then
Yes, sir.
Yes, sir.
you have the detector, which is somewhere here, and the separation between these two is, well, let me denote it by capital D, right?
Yes, sir.
You denote it by capital D, and the separation between the slits, this separation I will denote as a small d. Okay. Now, if you think of waves traveling like this, sorry, that is not a good line. Sorry, neither is it a good line. Sorry, I need to write. Okay, is that fine? So if you think of
Yes,
a
sir.
point somewhere here, you
Yes, sir.
see the waves which have traveled through this slit will arrive there. The waves which have traveled through that slit will also arrive there. And in fact, if you compare this path length with that path length, you will realize the way I have chosen this point, the path lengths are the same, correct? And if they follow the
Yes.
same, the waves that are arriving there will be in phase, and therefore they will exhibit constructive interference,
Difference.
right? And that is what is happening at this for this peak. Agreed?
Yes, sir.
Okay. And then let me rub off these two lines. Now, what is going to happen is if you think of another point somewhere here, then the waves arriving there would be going like that. Fine? Agreed?
Yes, sir.
And then you
Yes,
see
sir.
the length of this path and the length of that path are not the same.
Yes, sir.
And so, if the path length, if the difference in the length of this path and that path are different, there will be constructive interference only if the path length difference is equal to an integral multiple of wavelengths. So therefore, path length difference actually is equal to n lambda. And if you are thinking of the way it is, you see you have the big peak like here, then you have another peak, small peak, and another small peak. That is the way the experimental observation is. So this actually corresponds to zero path length. This peak corresponds to zero path length difference. That means it is equal to, it is having n is equal to 0 because the path length difference is 0. While this one we would expect it corresponds to n is equal to 1. So therefore the path difference actually is nothing but lambda. As far as this peak is concerned, the path difference is lambda. And how much is the path difference? Well, let me draw a perpendicular. I'll use a different color. I will draw a perpendicular like that. So a perpendicular like that. I will also draw another perpendicular in this fashion. And then this angle, you see, it is very small because this separation, this separation D is actually 100 nanometers. So that separation is 100 nanometers, and this separation, as I have told you, this separation is quite a large number. It is equal to, I have denoted it as capital D, and it is equal to 1.25 meters. So you see, this is a distances of the order of meters, while the separation between the two slits is very small. It is only 100 nanometers. As a result, you see, if you think of this angle, you would expect that that angle, we will call it theta, that angle will be rather small, very small. And if that angle is theta, then what about this angle? Remember, this is perpendicular to the two slits. This line is perpendicular to the two slits, and therefore the entire angle, this angle is 90 degrees. And therefore, if I ask you how much is this angle, then you will say that that angle is actually 90 minus theta.
Theta.
And if you wanted to calculate this side of the triangle, let me mark that, this side of the triangle, I want to calculate. How will I calculate that? I can use triple trigonometry. It will be equal to, this is, I'm calculating the path length.
Sine 90 minus theta.
Is it sine? You think about it.
No.
It is, what is it? I mean, what you have thought in the correct direction, but you see this part, this one is the hypotenuse, and that is the angle 90 minus theta. So therefore, the hypotenuse, which is equal to D into cos 90 minus theta, will be the path length difference. So, and this must be equal to lambda. Is that fine? Yeah, well, we see one of you keep unmuted and he should be answering, otherwise I cannot proceed. So is that clear? Because
Yes,
I
sir.
consider this one and that one, they are at 90 degrees to each other, because that is how I have dropped the perpendicular. And so it is a
Yes, sir.
right angle triangle, and all that I am using is trigonometric relationships to write the value of lambda, and lambda is equal to 90 into cos 90 minus theta. And cos 90 minus theta is actually sine theta, so therefore you
Sine
will
theta.
get the
Yes, sir.
lambda is equal to sine theta. Now what I want to do is I want to think of this distance. This distance is how much? 1.25 meters.
1.25. Yes, sir.
And this angle is 90 degrees. So therefore, if I wanted to calculate this distance, that is actually where you have the first peak. Okay, 1 second. So you see, right behind this part is actually, if I drew a perpendicular like that, this is actually again 1.25 meters. So now what will happen? You see, I want to calculate d sine theta. Sine theta is actually, if theta is very small, sine theta is approximately tan theta. Is that fine?
Yes, sir.
So this essentially means that you see tan theta, as you know, is sine theta by cos theta.
I cos theta. Yes.
But when theta is very small, cos theta is 1. So therefore, tan theta is approximately equal to sine theta. And because the angle is very small, you
Yes.
can use this approximation. So therefore, how much is tan theta from the figure?
Lambda by 2.
Lambda.
Yeah, well, you see, if you look at not lambda by 2, but the way I have drawn, you have the first peak and you have this is the first diffraction peak, that is the second diffraction peak. And therefore, if you say that this separation is the separation between these two peaks, correct? That separation is a separation between these two peaks. Then let me call it, what is the notation for it? Let me call it S, because that is a separation. So tan theta will be equal to S divided by how much? Tan theta is opposite side by adjacent side. Opposite side is equal to S, and the adjacent side is 1.25 meters. Is that fine? And therefore d sine theta is actually, because sine theta is approximately tan theta, and tan theta is S divided by 1.25 meters. So therefore d into S divided by 1.25 meters will be the formula connecting lambda with the separation, right? So therefore, this is the equation that you have to use. Lambda is equal to d into S divided by 1.25 meters. Fine. And how much is d? D is actually the separation between the two slits, that is actually 100 nanometers, correct?
Yes, sir.
So 100 into S divided by 1.25 meters is equal to the wavelength. And so what is the wavelength that we have calculated? Can you tell me the wavelength? I had shown it to you.
3.33.
I had shown it to you earlier.
3.3.
So
Three.
therefore
3.3.
3.3
3390
3390 into 10 to the power of minus 12 meters. So therefore 3.33902 into 10 to the power of minus 12, okay, this one is equal to 100 nanometers into S. S is the separation that we want to calculate, divided by 1.25 meters. So that is an equation you can easily solve for S, and you will get the value for S. Is that clear? And that is what you have to calculate and compare with the experiment. So having given this method, what I'll do is the rest of the calculation, I shall leave it as an exercise for you to work out. You calculate the separation. What is the separation? This is the separation. This separation between the peak on the left hand side and the peak on the right hand side is experimentally found to be some value which is available. It was shown in the picture, but now I don't know where that screen was, but it doesn't matter. If you look at okay. If you look at this, you see this is how it is. And so you have the horizontal axis. The horizontal axis scale is given here. And so from the experimental data, you have to find, using the figure, you have to find that distance and compare it with the lambda value that not with the lambda value, but the value of S that you have calculated. Is that fine?
Yes, sir.
Yes,
So
sir.
therefore, please do that and compare and tell me how the two compare in the next discussion session. Yes?
Yes, sir.
Okay, Aparna,
Yes.
now I will hand over to you. I shall stop sharing my screen, and you should be able to share the screen.
Yes. Sir, can you see my screen actually?
Yes, I can see it. No
Yes.
problems.
Okay, sir. Sir, before going into the discussion, I just wanted to make a few comments regarding the presentation of the paper by the students actually. So when we compare the grades, the presentation wise, it's like most of the students have gone down from the previous marks what they have obtained. And for me it is getting very difficult when the students are mixing up the questions. So if they try to write the questions in the proper order, then it will be very easy for me for the evaluation actually.
Yeah, well, you see, this is a point that the students should not. When you answer, please write in the serial order in which questions are asked. If you do not know the answer to a particular question, what you do is you put the number of the question and then leave a blank space, right? Leave a half a page blank space, you leave it there in case you are able to complete it later on, you can then fill it up.
Yes, sir. So this time I think like because of the mixing up, maybe there is a few from my side also for the valuation. So
Yeah,
I'm
students, see, this is all done online. It is not as easy as doing an evaluation of answers written on paper. So therefore, things are difficult. Unless you do what we tell you, it is extremely difficult. So therefore, that is your first comment. Is there anything more, Aparna?
no, so mainly this one and actually last time we discussed that instead of writing to the point, so most of the students are writing in elaborate. At the end, what happens is that many have lost the contact with the what they have started from. So at the end, they will be scoring 0 marks because they are deviating from the answer. So please make sure that they write answers for the proper question. Not like they write whatever they want, and this exceeds the file size also. That is why many of the students are having problem with the file size. They are writing more than that is required for the question. So that we mentioned last time, but this time also I think many have made that. And at the end, like what happens is when they write the answer, they will deviate and it is not, it cannot be evaluated because it is away from the key point. So that also to be done. So that are the few comments that I had to make. Hello, sir.
Yes, it's fine. If the students have anything to say, let them.
Yes, sir.
Okay, we will assume that there are no comments. So please proceed.
Okay, sir. Uh, sir, like I just wanted to for the answers they have presented.
Yeah.
Say, most of the students have made error with the 12th question. So I just wanted to start the discussion from that because
Error with?
9 mistakes with the 12th question.
Okay, what was the 12th question?
I can,
Okay, I can find out. Let me see. See, I have to open another window. That is the problem.
sir, it is there, but I am not able to.
Yeah, well, you see, don't worry. I'll get the question. Okay, here I have the question. Now I have opened. 12th question is actually hydrogen. Okay, this is an interesting question actually.
Yes, sir.
So I will share my screen temporarily so that I can explain the question. 1 second. Okay, you can
Let
see
me
my.
stop.
You can, yeah, what is which is the screen that you are seeing now? Students, please answer.
Pure white screen. Yeah.
Okay, so Aparna, then that is okay. I can stop sharing and then viewers must come back. Aparna,
Okay,
are
sir.
you? Yeah.
Yes, sir. Yes, sir.
Okay.
Yes, sir. I'm listening. Sir,
So
I have opened the question.
I can see the question. Well, if you want, I
Okay,
can put the question on the screen.
sir, as you wish, sir.
Huh?
Either we can, either I can share the screen or I can like.
No. I want to draw something so that I want to explain something.
Okay.
So therefore, I am going to share the. I mean, I am going
Yes, sir.
to take over the screen for some time.
Okay, sir.
See, if you remember, you have studied something called the Thomson model of the atom. Correct? According to the Thomson model, what happened was, I hope you can see what I am drawing.
Sphere.
It was assumed to be a charged sphere, and then there were, I don't remember, proton. Okay, one maybe let us say the
Rays were electron.
spheres were electrons. Okay, so therefore this is negatively charged, and then
The cloud was positively charged at
and
the
then
resins.
there was positive charge embedded, right? These are
No, sir.
proton.
Embedded are electrons, a negative charge.
It was inverse.
Negative charge embedded.
Okay, no problem. I don't remember this. Negative charge is embedded, so therefore these are
Yes,
negative,
sir.
and the sphere itself is positively charged.
Yes, sir.
Fine. So that is the model.
Yes.
Now this particular question question is asking you to do a quantum Bohr quantization calculation for such a model. So that actually means that this sphere would have a radius of capital R and a total mass which we will denote as m. Is that fine? So then I need to calculate the energy of the sphere according to the Bohr theory. Now, according to the Bohr theory, the angular momentum is I into omega, right? Where I is the moment of inertia and omega is the angular velocity. So that is angular momentum. And Bohr theory says that this angular momentum must be an integral multiple of h cross, right? This is what Bohr theory says.
Yes, sir.
So therefore, if you wanted to calculate the rotational energy of this sphere, rotational energy, as you know, according to classical mechanics, it is given by half into
Half I omega
I
square.
omega square. which may also be written as 1 by 2I into I omega the whole square. And I omega is the angular momentum, so therefore this energy E rotational will be 1 by 2I into I omega the whole square, which will be n square
L square
h cross square
square.
divided by, oh, there is nothing more, right? N square h cross square.
Yes.
Now, what is the moment of inertia? Well, you can find the moment of inertia from your physics BSc classes. Moment of inertia I of a sphere is actually 2
2
by
by
5
5 mr square.
mass into r square. So therefore, E
Yes.
rotational will be given by, you substitute for 2I, so n square h cross square by 2 into 2
By 5 mr square.
m r square by 5. And that must be the answer given in the question. The answer is given in the
Yes.
question, right?
Yes,
Are
sir.
the two? Are
Yes,
the two?
sir.
No, there is a difference.
5, sir, we have
H
to
and
open
H. We have
H
to replace cross by H.
by 2 pi.
Oh yeah, that is true. Thank you. Makes me very happy. So therefore, h cross actually is 2 h divided by 2 pi.
2 pi.
And if you
Yes, sir.
substituted that, you will get the answer given in the question. Fine.
Right, sir.
So this is how
Yes,
you have to
sir.
do the calculation. But then, of course, that is only the part of it. Then just like the Bohr theory in which you calculate the energy required for transition from n is equal to 1 to n is equal to 2, right? While what
Yes,
will
sir.
you do? You will, you have this
E2 minus E1.
yes, you will have this rotational energy. It is dependent upon a quantum number n. So therefore, you have to calculate E2 minus E1 and divide it by h, and then you will get the energy of the light. Sorry, not the energy, but the frequency of the light, which will bring about that transition. And I also want to make another comment. The comment is the following. Allowed energy levels are given by n is equal to n square h cross square divided by 4m r square into 5. These are the allowed energy levels. And so if you say n is equal to 1, you will have an energy which is, let us say, so much. Then if you put n is equal to 2, you will get another energy which is like that. And this separation is E2 minus E1. And the next allowed energy level is actually somewhere here where it is 9 h cross square by 4m r square. Fine. So therefore,
Right.
if you look at the allowed energy levels, you find that the separation, this separation is actually smaller than that separation.
Yes, sir.
Yes. And when
Yes,
the value of n increases, what will happen is that you will get another energy level. Let me just throw it here. Unfortunately, it is mixed up with other things. So if this is the next energy level, this separation will be even larger. So therefore, if this was the way the energy levels were, the successive absorptions will happen at very high frequencies. Whereas if you, do you know what will happen if you use the Rutherford atom model and use the Bohr quantization? The answer is that you get allowed energy levels. This is the first allowed energy level. That will be the second allowed energy level. The third energy level is actually closer.
Sir, inverse relation with the n value of n.
So this is the first energy level. This is the second energy level. That is the third one. The next is even closer, and the next is even closer. So therefore, this is actually the correct result. While this model, that is actually the Thomson atom model, gives you completely wrong prediction. So that is what I wanted to say. That is the first thing. Then there is one more thing that I want to say. There was the first question in the assignment that you were doing. Second, that actually means first question. The second assignment is asking you to explain the relationship MVR is equal to NH cross. How do you want to explain this? Well, the answer is that you want to use de Broglie relationship. What does de Broglie relationship say? It says that lambda is equal to h by p,
MV.
which is h by mv. And now you let me draw a circle. You see, according to the Bohr theory, the orbits are circles, and r is the radius of the circle, and therefore the circumference of the circle is actually 2 pi r. And if you think of a wave going around it, right? If you think of a wave going around it, oh, sorry, it needs a little bit of carefulness to draw the wave. If you say that, okay, there is a wave going like that. And you look at what I have drawn, the wave, when it is going around, it will come back, and at this point it will produce a displacement which is opposite to the original displacement. So therefore what will happen is that the initial part of the wave will interfere with the final part, and there will be destructive interference, and therefore this kind of wave cannot exist on a circle. So what is the kind of wave that can exist? The kind of wave that can exist is actually, let me try to draw it carefully. Right? So therefore, this is what will happen. Notice if you counted the number of wavelengths, you see this is a wavelength. This is another wavelength from here to there. This is another wavelength from there to there. This is another wavelength from here to here. And then you have another wavelength. So therefore, what happens is that the circumference is actually an integral multiple of the wavelength. Then only the standing wave pattern can exist. And therefore, what is the condition? Lambda must, n lambda must be equal to 2 pi r. Is that clear?
Yes, sir.
And how much is this? That is actually n into h divided by m into v. And if you rearrange, you will get mvr is equal to nh by 2 pi, and therefore you will get this is actually equal to nh cross. That is the Bohr quantization condition, and this is actually the first problem that Aparna will talk about. Is that fine?
Sir,
now I'll stop my sharing.
Sir, can you hear me, sir?
Yeah, I can.
Sir, sir, one of the student, she lost the connection actually, Sulekha. Please
Yeah, well,
add
I have to admit her. She is waiting. You could have admitted
Yes,
her
sir.
because I think I have made you. Oh no. Okay.
No, sir, no, sir, no, sir.
Okay. So I have admitted her. So she should have joined.
Yeah, she's not here. Yeah, she's there.
Okay, go ahead and discuss. I don't think I need to explain anything more. If you need me to explain anything, I will explain. I'm here. I haven't gone away.
Okay, all right, sir. Sir, I thought like these questions 9, 10 and 11, so you have already explained it. So, and there was not much mistakes from the student side also. So I don't think that they have some doubts. So if they have any doubts, let's discuss or we'll go to the question number 12. You have explained detail. So I was thinking that we will focus on the questions which were which most of the students made mistakes.
Okay.
So one was question number 12
Yeah.
and the next was question number 13.
Okay.
So to 12, the problem was that even though the question is given, so they were not aware of how to come up with this kind of energy.
Okay.
Instead, they were trying to go with a one-dimensional problem and trying to solve in another way. So
Okay.
since you have explained the answer, I think the concept is clear for the students. And the rest of the answers I have given here. The final calculation, final results up to what the value should be, I have given it here, sir.
Yeah, well, you see, the major thing is actually in question number 13, you need to know the moment of inertia. You need to know the moment of inertia because you will say that I into omega is equal to nh cross, where h cross is h divided by 2 pi. That is the Bohr quantization condition.
And sir, here actually one of the student was asking whether they have to go with a one-dimensional problem. That is,
No. This is happening in 3 dimensions. This is really a rotational motion of a diatomic molecule in 3-dimensional space. Right?
yes,
So
sir.
therefore, you need to calculate the moment of inertia of the system. See, for example, in the other question that I discussed just now, I had given the moment of inertia for the sphere. And then we could complete the calculation. Similarly, in question number 13, you have to know the moment of inertia of the rotational motion. And that actually is given in the question itself, assuming the rotation to take place in a plane. And using Bohr quantization condition, find the allowed energy levels. So if it is rotating in a plane, okay, yeah, well, you see, the rotation is equivalent to rotational motion of a diatomic molecule is equivalent to that of a single molecule of mass mu. What I am doing is I am reading question number 13. Let me read it from the beginning. A model for the rotational motion of a diatomic molecule AB is to think of a single particle of mass mu Ma into Mb divided by Ma plus Mb. This is actually the reduced mass of the system following a circular path of radius r, where r is the bond length of the diatomic molecule. So therefore, for such a particle which is going around in a circle of radius r, about the origin, the moment of inertia is actually its mass into r square. So therefore, as far as this model for the diatomic molecule is concerned, the moment of inertia will be mu r square, which is Ma into Mb divided by Ma plus Mb into r square. So that is the moment of inertia, and therefore you can use the same procedure as in the case of the Thomson model and get an expression for the allowed energy levels. So Aparna, you can continue.
Okay,
Excuse me, ma'am.
Yes, tell me.
So in 12th question, the last part, for what value of n does the transition have a wavelength? So there, proton doesn't undergo transition now. So we have to take electron transition.
Where is it?
The last part of 12th.
Last part of 12. So, okay, so now what is the question?
So just before that, we have, it is asked that take m is equals to mass of proton. And it is then asked for what value of n would the transition take place. So here, so the transition we'll consider of electron.
No. You see, the way it happens in spectroscopy is you have a quantum mechanical system. You find the allowed energy levels of the system, and the allowed energy levels are quantized. They have the value E1, E2, E3, etc. Is that fine? See, for example, we just now I talked about the Thomson model, and there the allowed energy levels were given by what expression? The expression given in question number 12. And there you see that there is an allowed energy level. Aparna, can you just highlight? Oh no, you don't have the question with you, right? So
Sir,
therefore,
I have shared the screen actually, so you can see the question here.
yeah, okay. So therefore, the allowed energy levels, you just highlight that. Yeah, these are the allowed energy levels, and this n is a quantum number that takes the values 1, 2, 3, 4, etc. Correct?
Yes, sir.
So these will give you the allowed energy levels. And you are asked to calculate the energy of transition from n is equal to 1 to n is equal to 2, right? So that was the first part. But then you are asked, you see, what you have to do is, if the wavelength of the radiation is given to be 5,000 angstroms. So is there any value for n for which n to n plus 1 transition, that means the transition from nth state to n plus 1 state would have a wavelength of around 5,000. So you have to calculate the value of n. Is that clear?
Yes, sir. I was asking that we have to consider the transition for proton.
No, you have a sphere. See, in the Thomson model, there is no separate proton.
Okay.
So therefore, you will say that you have a solid sphere, and this solid sphere, according to quantum mechanics, have energy levels which are given by the Bohr quantization condition.
Yes, sir.
And so therefore, you find an expression for the allowed energy levels. And now imagine that there is a transition between n is one state and another state, having different energies. And imagine that that is induced by electromagnetic radiation. And so imagine I illuminate this sphere with a light of wavelength 5,000 angstroms. And imagine that there is a transition. That means, you see, your sphere was rotating with some speed, and then because of interaction with energy, it has gained some, with interaction with electromagnetic radiation, it has gained some energy, and therefore the rotational energy of the sphere has increased, and so it will go to a new quantum state. Okay, it will go from one quantum state. You see, it was rotating like this. If you look at my video, you can see my hand rotating. And then what is happening is that radiation comes in like that, right? And interacts with the sphere, and the sphere is now rotating faster, correct? I cannot show a full rotation, obviously, using my hand.
Yes,
So
sir.
therefore, as a result of interaction with radiation of 5,000 angstroms wavelength, the sphere, the solid sphere of Thomson model is rotating faster.
Thank you, sir.
Okay. Aparna, please continue.
Sir, Neela here.
Yes.
Sir, in question number 13, we have considered the two molecules to be as a single molecule of mass mu. So, do we have to consider center of mass as that molecule, that single molecule that we are considering?
Yeah, well, you see, it is not a, I mean, there are some mistakes in what you said. We have a diatomic molecule. The diatomic molecule has two atoms, right? And these two atoms are at a distance of capital
Yes.
R. Now you will study
Yes, sir.
later when we discuss quantum mechanics. You will see that the rotational motion of such a diatomic molecule is equivalent to the rotational motion of one mass whose value is actually equal to mu. So therefore, rotational motion of a diatomic molecule, which actually has two particles, is equivalent to the rotational motion of a single particle of mass which is equal to the reduced mass of the molecule. And the distance of that particle from the origin being equal to the length of the diatomic molecule. This is something that hopefully will be discussed in spectroscopy as you go in further detail. So the question actually gives you all the details that you need. What I said, the rotational motion of the diatomic molecule is equivalent to that of a single particle of mass mu going around the origin along a circular path having a radius which is equal to the bond length. So therefore the question is self-contained. All that you need to do is apply the Bohr quantization condition. First of all, you find the moment of inertia I. I is equal to reduced mass into the distance r square, distance square actually. And so you have the expression for the moment of inertia. Once you get moment of inertia, you follow the procedure in question number 12. And you will get the allowed energy levels. Is that okay?
Okay, sir.
Okay, fine. Thank you.
Okay, sir.
Aparna?
Yes, sir. So I think sir, next question is the 15th question, sir. Because the path integral that is that entire question answer can be obtained from your video lecture.
Okay.
So that entire answer is there in what you have described in that video lecture.
And
I
have
think.
the students answered it correctly?
Yes, sir. Yes, sir. That has they have well defined the answer, so that's why I don't want to highlight.
Okay, so that means I'm happy because you see, they are watching the lectures and understanding them.
Yes, sir. They have perfectly answered. Actually, I think only one or two only might have made some mistakes, but the rest.
Okay, the questions number 15 and 16. Actually, in principle, you see, these are quite simple because what you are expected to do is look up a textbook, some textbook, get the answer from that textbook. So this is an exercise which I have put so that you will get familiar with looking up expressions. Now you may even find the answers in Wikipedia. You must be familiar with Wikipedia, and so does everyone know about Wikipedia?
Yes, sir.
So the answers to these questions you should be able to find from the web, or what you do is, you see, for example, it may be found in some physical chemistry textbooks. A textbook like Daniels Alberti. No, it is not Daniels Alberti anymore. It is Daniels Silby and somebody else.
Silby and Albert.
Silby and Bawande, right?
Alberti.
Sorry?
Silby and Albert.
No. It is maybe Albert, Silby, and Bawandi. These are the three names. So you look into that book, you may find the answer. Or if you don't find it, you search for some book where the answer is available. So therefore, what I'll do is 15 and 16, I will still keep the exercises, let them find it, because it's essentially searching for some information and getting it from the web or from some book. I will discuss it anyway. We have run out of time because it is already 6 minutes past 3. And therefore, if I discussed it, it will take a little bit of time. So in fact, I have written down the answers, but I suggest that you please have a look at the sources that are available to you. Get familiar with looking up information and then find the information and come back next for the next discussion session with the answers.
Sir, for the next discussion, we have uploaded the assignment 3 also. So I think for that it will take less time only. So we will get enough time to discuss these.
Okay, that is great.
So it's 7 questions. So
now the question number 17, I should tell you, Aparna, can you lift it up a little bit so that I can see question number 17? Yeah, well, you see, this is a mistake on my part. I should have said point out the similarities between um, the
Questions.
essentially it is actually the similarities between the quantum mechanical expression for the path integral and perhaps an expression for the drunken walker. I will consider this question as deleted, and I will perhaps put the similar question later on.
So we can include this question in the assignment 3. Actually, so, no students have submitted.
Okay, okay, fine.
So we can include this question in the
Yeah,
assignment 3.
okay.
Yes, sir.
Now, any other thing that we should discuss?
And this question number 18 has to be also discussed in actually many students were making mistakes with question number 18. So that it will take more time because that we can, so some portion of question number 18 is again repeating in assignment 3 also. So we, if possible, we will discuss these questions in the next session.
Students, I assume you are happy with that?
Yes, sir.
In that case, we are going to close, but somebody wants to ask a question, so please go
Yes,
ahead.
sir. Sir, Akash this side. Sir,
Yeah,
I
okay.
want to ask like in order to in the Hamiltonian when we want to describe potential energy, like uh, should we write directly Vx or like we define electrostatic or the different types of
Yeah, well, it depends upon the problem. Aparna,
like H2
can you
plus.
just go up in the question?
So I think they are discussing the question number 18 itself.
I understand, but there must be more to the question, right? This is the
Sir,
only
it
thing.
is specifically regarding H2 plus.
No. You show me the answer. Yeah, okay. For example, you have the energy of H2 plus. That's why I wanted you to go up. Okay. No. Don't show me the answers. I need only the question.
Oh, okay, sir. There's a problem.
Yeah. Well, maybe I can use this answer. Oh, now you have changed it. Okay. Now.
Yeah, this one. So
No. You keep it at what a particular. Okay. See, for example, in the case of this particular question, unfortunately, I cannot highlight because it is your screen.
Sir, I can see.
Yeah, well, Aparna, can you lift it up a little bit because I cannot see the full question. No, the full answer. Yeah, okay.
It will stop at this point, sir.
Okay. Now, if you look at the value of the Hamiltonian, the operator, then you will see that there are kinetic energy terms which are perfectly right, I think.
Yes,
I'm
sir.
saying right, I think, because I cannot see the lower portion. Then you have the potential energy. The potential energy is given by these terms. You see 1, 2, 3, three kinetic energy terms. Then you have the potential
Yes, sir.
energy of the system. So therefore here the potential energy actually is dependent upon RA, RB and RAB.
Sir, so,
Now,
here we are considering electrostatic potential energy.
yes, so it is given that you are thinking of H2 plus molecule.
Okay, sir. So depending upon the case.
Depending upon your problem, the expression for potential energy will be different.
Okay,
For
sir.
example, for a harmonic oscillator, the potential energy is given by half
kx
x
square.
square. So if you are asked to write down the Hamiltonian for a harmonic oscillator, then you have to use that expression for the potential energy.
Okay, sir.
So it will vary depending upon what the problem is.
Okay, sir.
Okay.
Yes, sir. Thank you, sir.
Okay. Is there anybody else who wants an urgent answer? Otherwise, we will meet in the next tutorial session. Okay. Now, let me repeat the announcements that I made in the morning. The announcement was that you see you have to be reporting in time for this, for the discussions and classes, I will modify that and say that you have to report 5 minutes earlier. Because you see, today, for example, I started, I joined in at 1:50, and there was only one student or two students, but that doesn't matter. And then up to 5 minutes past 2, people were coming in. So please don't do that. Please report before the 5 minutes before the session starts, so that we can start the session on time. You see, these sessions are taking too much time. So therefore, I want to get as much time as is possible for the discussion.
Okay, sir.
That is the first thing. The second thing is actually, remember you have a quiz. Usually we refer to the test as quiz. So therefore, you are going to have a quiz on Friday at 9:30 a.m. Please be on time. You have to be here at 9:30.
Yes, sir.
Okay, there is another way in which I can conduct the test. Let me just think. Aparna, is it possible to upload the answers on the Moodle?
Yes, sir. If we set the time, they can upload it within that time.
Okay, you can set the time. So therefore,
Yes,
let me tell you what is going to happen. At 9:30, I will share my screen and you will see the question. But you will not see the full question paper. You will see only half the question paper. At 9:45, I will show you the other half of the question paper.
Okay, sir.
And 10 o'clock, you have to finish writing.
Okay, sir.
And immediately you have to upload it in Moodle. And by 10:05, you should have done the uploading.
Okay, sir.
So you see, the idea is that when we conduct tests online, it has been my experience that the people try to share information. This is happening. So therefore, I don't want that to happen, and that is the reason why you will be shown only part of the question in the beginning, so that you are forced to answer that question. You cannot go anywhere else. And then after half time, that means after 15 minutes, I will show you the other part of the question, so then you can answer that question. And as soon as you finish, you upload it in Moodle. Fine?
Yes, sir.
Yeah, I'm sorry, this is all quite complicated. Unfortunately, it would have been much better if you were here physically in the campus and I was talking to you in the classroom. I believe classes would have been more effective, but unfortunately, COVID is preventing us from doing any such thing. I'm sorry,
Yes, sir.
but you understand the situation. For our own safety, we have to keep the distance. And in the case of this class, you see the distance is large enough. The virus simply cannot be transmitted. Okay.
Yes.
Okay, then I'm going to close the meeting. I have put the lecture for recording. Somehow it keeps on disappearing. So therefore, I don't know. Let me see whether the recording is there. If the recording is there, where should I upload it? Is it possible to upload it in Moodle, Aparna?
That we have to look, sir. It's like, I
Okay.
think,
Yeah. Well, you see, I
uh,
have a YouTube channel. So therefore, I will give you the link to my YouTube channel. You can look at the channel and look at it, and you will see the recording. That would be easier.
Sure.
Okay. Fine then. Thank you. I will end the meeting for all of you.
yes. Okay, right. Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.